Well, good day, everyone. I'm gonna welcome you to our last suite of lectures for the semester. And what we're going to talk about today is mineral resources. So mineral resources are an incredibly important part of the geological sciences, as well as the value chain for most of the things that happen in society. What we're going to do first here is just classify Earth's mineral resources in general. Elements that elements for metal, which are required for metal production technology, are some of the most common types of earth mineral resources. Abundant examples include iron, aluminum, chromium, and manganese. Um, and for example, iron and aluminum alone account for about 3% by weight of all the materials mined in the U.S. in a given year. Some of the other things that are actually mineral resources in our mind, which people tend to forget about, are actually building materials such as sands, gravel, used for road aggregate, building constructions. This accounts for 94% by weight of all the minerals mined in the U.S. every year, and that number expands continuously. Those are actually becoming very precious resources around the world, as well as in the U.S. Other important components include minerals mined for the chemical industry. These can include minerals for production of petrochemicals, catalysts. To some extent, some of these things are even recovered from oil and gas reserves. And last but not least, people tend to forget that actually minerals for agriculture, particularly fertilizers, phosphatic fertilizers, account for about 1% by weight of all the minerals mined in the U.S. and are a really important mining component. This of which is actually becoming a pretty important, and critically limited resource. There aren't as many phosphate ores left to be harvested out there. So the role of minerals in our everyday lives is actually quite a lot larger than you might realize. If you look at probably your home office or your parents' home office where you're at today, if you look at everything in that room, I think the simplest way to describe it, rather than going through each one of these examples for you, is to say, if you can't grow it, you have to mine it, right? So if it's not grown as food or harvested from the sea or something like that as a fish or something like that, you pretty much, if it's not wood, it's been mined, and many aspects of the even wooden furniture have probably been mined. So you can't overstate the role of mineral resources in your daily life or in human survival. Another example of this is just looking at a smartphone. The smartphone, we all hear these things. These computers are held within the palm of your hand and are more powerful than the computers used to send humans to the moon, 5 decades ago. But the reality is that those smartphones aren't just a novel technology. They're actually an incredible compendium of various elements, batteries, like lithium components, casing a whole bunch of ranges, and particularly electronics. We'll talk about as a major focus of this lecture. Rare earth elements and used for electronics that have enabled this reduction in the size of the computing capacity and screens and whatnot. So all really important. If you think about mining from the perspective of how important it is to society, it is unfathomable. Every year in the United States alone, this number will go up every year. It's just like water, it's just like energy. Per capita usage increases all the time. On average, we consume about 769,000 pounds of new minerals provided for every person in the United States every year to make the things we use. Okay, so a good number. I'll give you this number to keep in your head for the exam. That means each person on average consumes more than 45,000 pounds of materials per year. A lot of that is stone, sand, aggregate, cement for buildings, roads, infrastructure. Can range down to salts that are essential for food and de-icing roads, all the way down to essential metals used in nutrients and minerals and things like that. I won't sit here and read this all to you, but I can't overestimate. You interact with the mining industry more than you interact with oil and gas, fossil fuel energy in ways you don't even realize. Okay, so much of it just in terms of infrastructure. And obviously, not every person's really using 45,000 pounds of materials, but our construction, our infrastructure is basically consuming that much on a per capita basis. So let's just look a little bit. Let's just look a little bit of how this, similar to all of our population growth curves, how this all changed in the last handful of years. From 1950 to 1990, as we've talked about before, the U.S. population grew by about 65%. But just like I said, with water and with energy, the per capita energy use actually grew by 130%. Basically, per person, we use twice as much materials as we did in the generations leading up to that time. So this is of course a major change in the amount of material per use, and we've moved to, as we talked about already, a much more consumptive society in the process of this, the process of becoming modernized. And you can look at the homes, you can look at the highways. Just think every single bit of this road has all been a mine. Every one of these barrier signs and most of the material in these cars, they're all mined materials that come from somewhere. They might be recycled, but they're still heavily mined from new resources all the time. So, by in 2003, it was estimated that every year, every American would, over a lifetime, consume about 3.5 million pounds of mineral and fuel resources. The 2020 estimates of that aren't in, quite frankly. It's why that's the last time I've seen that this statistic calculated. But the estimates are over about 4 million pounds of minerals and fuel resources today, compared to just even 20 years, nominally 20 years ago. Looking at the mineral resource, it's an area where America really looks like big consumers. I've mentioned in the last set of lectures on fossil fuels, we've actually seen a decrease in the amount of CO2 emissions. When it comes to actually consuming mined resources and the resources for infrastructure for electronics, we are not seeing any decreases yet at all. We are in a huge consumer mode. Cell phones, laptops, all these things add up. We make up about 4.5% of the world's population in 2002. That's about the same percentage now, and yet Americans consume, much more than 4.5%. Up, in some cases, above 25, 50% of key resources such as lead, phosphate, cobalt, and other metals. One of these things that's actually removed in here, lithium. Us and China are basically now the biggest consumers of electronic cars, lithium batteries, and as a result, there are things where the percentage is even getting higher and higher and higher as we're going up. We're not seeing a rollover as we did with power consumption. So let's think about this just from the basic perspective. What is the basics of mineral resources? What's an ore? An ore is a rock in which a valuable or useful material, could be a metal, could be road aggregate, occurs at a sufficiently high concentration relative to the average rocks around it to make it economically worth mining. So what's important here is that I can go out, mine a cubic meter of rock, and I might be able to find gold in there, find a gold nugget in there amongst the total. But if that gold's not concentrated to the point where I can pull it out in an extractable economic fashion, it's not an ore deposit. However, if I find a little band of metal-rich, intrusive rock, or what we call an ore deposit, that has a high amounts of something like copper in it, and I can harvest that out really easily and send that back for processing, it could be an economic ore deposit. There are two major factors in determining the profitability of mining an ore. The first is quite simply the spot price of the value of the mineral or metal being extracted. If you were out there trying to determine, and you found a lithium mine, 1950, the price of that lithium would have been pretty darn low, not really worth much at all. Today, electronic cars, batteries, energy storage needs, lithium is a hot commodity. Today, that spot price would be pretty high. So certain things weren't really considered ores, or not very successful ores, and now in other cases are considered to be pretty economical as an ore. The second factor, so it's just how concentrated it is. The second factor is how concentrated, or the value of the ore. And the second one is just how concentrated ore is in the rock deposit. So again, the higher the concentration, the better. The higher the spot price is better. If you look around, a lot of as an example, a lot of the key ores, something like gold, its percentage in the Earth's crust is in the part per billion range, maybe 40 parts per billion range. If you look at it in ores, it can be in the parts per thousand range. These are enrichments in gold deposits about 2,500 times. It's the only way you're ever going to recover it, economically. Similar, the numbers change, but the suspects remain the same. Similar levels of enrichment in many ore deposits, although gold, mercury are amongst the most enriched in the ores compared to natural backgrounds. So the key aspect of all this, of course, is that this gives you a sense of the approximate concentration you need to have an economic ore. But again, ore is something that's a valuable or useful, it could be a metal or other resource at sufficiently high concentration. And whether that concentration is sufficiently high is partly going to depend upon the economics. You need both of those things to have a successful ore deposit, valuable of the material, the mineral and material, and elevated concentrations. So this just gives you an image of the relative concentrations of various things. On Earth, this is normalized to the atoms, normalized to silica, to the bulk silica at Earth. As you can see, most of these things up here, oxygen, carbon, hydrogen, silica, of course, is 1-to-1 by definition. Calcium, these are things that are essential nutrients for life. But with the exception of iron, most of these are not actually going to be extremely valuable ores. The ones that sort of fall into this range, iron and aluminum, are things that are so heavily used that they actually still have some value, but you notice their price points are nowhere near the price of gold or anything like that. Comparisons you see as you go down the relative enrichment, as these things are more and more depleted with increasing mass along this periodic table, you'll notice that in general the price tends to increase, per unit of mass as you move further down this range of concentrations. And then, despite the fact that we call rare earth elements rare earths, what we'll get to later, they're actually not that infrequent. They actually occur, not only high concentrations, they're just distributed around and aren't really concentrated in ore deposits. Some of the more precious or rarest metals, things like palladium, platinum, are actually far more rare than the elements we dubiously call rare earth elements. As a result, they are of great importance. But as you can see here, major industrial metals, there are things that occur in high concentrations down to low concentrations. Precious metals tend to be things that are really restricted in terms of their concentration. And here are the rare earth elements, which we'll talk about more in a minute, are in blue. The key thing to remember here is rare earth, mineral resources. Rare earth is an example. They are not distributed evenly around the world. Geology is placed in certain areas. Most geology happens where plate boundaries either have convergent, divergent, or transform processes, particularly convergent and divergent for mineral resources. And a result, those geological phenomena, broadly speaking, over hundreds of years of economic geology, concentrate these ores in certain areas. Okay, so for example, the United States basically contains 60% of the world's molybdenum, 40% of the world's lead, and basically almost none of the world's aluminum. For example, we use 30 to 40% of all the world's aluminum. Okay, but there's clearly an imbalance between what we need and what we use. For comparison, we have almost no, very trivial amounts of cobalt. Less than almost 0% on a global scale. But in countries like Zaire and Zambia, Democratic Republic of Congo, contain about 50% of the world's cobalt and are major coltan miners of cobalt ore that export these to other parts of the world. So for example, South Africa, relatively small country in terms of GDP or total population, accounts for about 40 to 50% of the world's gold, 75% of its chromium, 40% of its platinum. So this can be very asymmetric, and where it's mined is not necessarily where it's used. This is for perspective in terms of where it comes from. You notice we're relevant in iron, but small, especially compared to Russia. Aluminum, we have almost no relevant percentage. Copper and gold, we matter, but most of the gold mining is occurring in South Africa and emerging in other locations, but not really the U.S. So this gives you percentage minerals that the U.S. imports. We would basically be importing in this graph, the vast majority of our needs. So basically, most of our minerals are imported. In fact, the U.S. is very, very limited number of elements we're actually self-sufficient in, such as talc and feldspar, a little bit of iron slag. So one of the hot topics in rare earth elements, in mineral resources, rather than trying to cover all of them, I'm going to cover is rare earth elements. Rare earth elements is a big, important, particular type of mineral deposit. The biggest issue with rare earth elements is it's extensively used in modern electronics, smartphones, electric cars, weapon systems, and wind turbines. If you want to know why your phone's getting so expensive, it's because it has so many rare earth elements in it. As a result of the fact that the world's going electronic, computerized, digital, there are increasing demands for rare earth elements for all these purposes. It's quite an interesting case study into how mineral resources, geopolitics, environmental damage can really very directly overlap. I won't sit here and read these all to you again, but they're here for your interest. You want to look up this more. Each of these rare earth elements, some are used for other purposes. Gadolinium is commonly used for medical imaging and anti-cancer drugs, but all of them are in various parts of the speakers, circuitry, color screen, etc., in diodes of your smartphone and other electronics, not just phones, but TVs and whatnot. As I alluded to earlier, rare earth elements are considered rare, which is a total misnomer. If you remember that back to that periodic table right up here at table, but that graph of elements according to mass. Now they were pretty high, sort of in the middle range. The issue is that the rare earth elements are not concentrated in any ore deposits. They're basically, cerium is the 25th most abundant of the 92 naturally occurring elements. So it's, the top third actually of most abundant elements. But they're typically dispersed and not found in concentrated ore deposits, and as a result of that, just simply do not get, cannot be found in porphyries or other igneous intrusions or geothermal epithermal deposits, something like that, where concentrate things like copper and zinc and other things that can be mined. The other issue that makes rare earth elements so intriguing is that 97% of the world's population, the world's production for rare earth elements comes from one country, in China. As a result, it's been a very powerful geopolitical tool for them, and it's been an area of pretty direct concern for a lot of the other competing nations who need to have access to this resource to do electronics, computing, and other things like that. So, they basically have a bunch of sand deposits that are rich rare earth elements, and more so than most of the countries in those regions, they have very relaxed policies about the manner in which the rare earth elements are mined, the strategies for leaching with hot acids and stuff like that that can remove these materials. But as a result, they control a lot of this. The U.S. GS reports the U.S. has about 13 million metric tons of rare earth elements. There isn't many active rare earth element mines left in the United States. A few in Colorado and a few in California, but by and large, we're pretty limited, and so is most of the rest of the world. There's predicted shortages in the future. As recently as 2009, it's predicted the demand could outstrip supply by 40,000 tons annually in the next decade. We're there now. The reality is that the prices went up. People went deeper and further and extracted lower concentration ores. But the reality is that we've so far managed to meet the supply with the prices increased dramatically. And there is going to be a sustainability question that comes up here at some point, both in terms of the methods we're using to get them now and the extreme costs, both the human lives and in economic dollars. So there's been a move towards more what's called artisanal mining, small scale operators. Could be something small as 2-3 people, as big as a cartel of a small company, often working without in the more poverty-stricken countries, often without the sort of normal level of oversight you'd expect to see in some places like the U.S., Canada, or Australia that have very well regulated mining industries. So we're reaching a tipping point with rare earth elements for sure. And there's of course always aspects of trying to recycle these, minimize the amount of these materials that won't be lost to landfills. They want to make sure these come to areas where they can be properly recycled, minimize environmental damage, and of course, it's a geopolitical football if we let somebody, one country, have all the resources. So again, just to remind you, this is sort of in the middle of the range, but it's so important because of the electronics applications. Just to give you a sense of the geopolitics, in 2011, China began using rare earth elements as a pretty strong political tool. Neodymium is one of these rare earth elements. I'll just go back here a second. Neodymium is one of these rare earth elements right in the middle here. And basically, it was pretty important for making the Prius electric motors stronger and lighter. And just from the price point of 2009 to 2011, it increased by more than, I think almost 12 times here, from $15 a kilogram to $244 a kilogram in 2 years. And it's stayed around that range. It was bad timing for the U.S. in terms of the fact that our mines started to be exhausted. We started to stop being very relevant in rare earth element production, right as the dramatic increase in electronic uses occurred, and China was really there to take control and exploit that opportunity to their benefit. Other examples: dysprosium, very commonly used in lasers and various types of lamps. Similarly, almost a tenfold increase in that time frame. And then during this time, there was major disputes over fishing waters and land claims in the China Sea and Sea of Japan and whatnot. And at that time, China decided to cut off supplies to Japan, which is heavily involved in electronics manufacturing, as a way to dispute that, settle that dispute of the fishing waters. So these activities have led to increased activity in the U.S. as well as other locations to identify rare earth elements, identify more efficient processes for refining them or recycling them, reusing them, all the big R's there. But without any ambiguity. The prices of these spiked around 2010 and 11, and then actually started to come back once people started, investing more money in the U.S. and Japan and other locations. Particularly Australia and Canada. And the Australia, Canada, and the U.S. have all ramped up rare earth element production quite dramatically, relaxed some of the regulations around harvesting those rare earth elements. As a result, the prices come back down, but it's remained well above the background, and it's actually probably come back up a little bit since these time frames. So, what are some of the problems with rare earth element mining and market manipulation? What does this actually do? Of course, the challenge here is that the manipulation of the market, just like any other resource, creates huge uncertainty and creates huge price increases temporarily, which disrupt product supply chains, disrupt companies that are working in this space, make people, uncertain about buying an electric car that they won't be able to repair or replace it, for example. The other aspect of these price swings is it actually led to some very severe environmental problems in China, right? It led to a huge growth of this artisanal or backyard operations, small scale operations. People are going out there finding potential rare earth element deposits. Maybe they weren't that rich in rare earth elements that we talked about, but they're relatively rich, and they would take risks in terms of mining them and trying to purify them. As a result, based on the fact that these artisanal mines are not necessarily legal, it's estimated today that about 40% of the rare earth elements, purchased in the last decade are actually be classified as illegal, certainly illegal in the United States. And it's important that those are minimized from the economy. So these operations have little concern for the environment. They're typically using sulfuric acid or other hot acid leaches. Those can themselves be very toxic to the workers. Often you can imagine here it's a slippery slope. They're using low-income, vulnerable populations. Many times the waste is just dumped in the back, and the streams and rivers downstream are pretty heavily polluted. And as a result, some of in like Baotao, China, where some of these areas where there's modestly enriched rare earth elements on certain types of clay deposits, there's pretty rampant environmental pollution. Clearly, the working conditions for employees are not particularly good, and they're working with chemicals that, quite frankly, if we were going to use them in our labs here at Ohio State, we'd have to wear personal protective equipment, work in a fume hood, and have redundant policies in place. Typically speaking, instead, what we're seeing is situations where it's more commonly, a bunch of acids, chemicals, and maybe a little fan blowing that away from you. These sort of small scale artisanal mines are not exactly what we'd like to see for safety. So I'm going to play a little video here about rare earth elements in China. So these are the waste effluents coming out of the refining process. So basically, they're taking raw ore. Again, ore is a misnomer here because they're not particularly concentrated in anything. They're taking clays that are modestly rich in rare earth elements. They're spurging it, basically flushing it or sparging it with hot acid volatilization, trying to concentrate the rare earth element resources. And then they're taking the acids, the waste ore deposits, and just basically making a slurry up in the other end of the plant. So you can see here, this is obviously covered with, waste ore, very acidified, talking pH of 1 here for most of these kind of stuff, pretty nasty stuff. these would all be, again, pretty acidic. Nothing's going to really ever grow here again. I'll just click forward. I think you probably get the sense of it, but it's pretty hard to realize the sort of even quantify the damage that would be done to the area from that type of mining, let alone the employees who are working with in smaller scale, non-lab, setup examples. So, the real aspect of this is that as a result, floods of rare earth elements onto the market from China has actually caused a price drop, which is of course against the sort of policy they were trying to have in place from a geopolitical perspective. Along with the U.S., Canada, and Australia, this caused everything to swing back down. As I mentioned, it's kind of swung back up. Now it's in a sort of intermediate phase, but it's been a rapidly volatile market where obviously you can imagine prices are down. People are purchasing as much as possible, and prices swing back up. Obviously, people are trying to stockpile this. That also manipulates the price. So you can basically look at this more on the Guardian if you want to. There's some good articles about this, about how the World Trade Organization had various complaints about quotas and price manipulation and all these different things. It's been a pretty volatile political issue, and one that I'm sure won't go away. Most of the export quotas have sort of been scrapped recently, and it's kind of calmed down a bit in the last few years with the intermediate prices after China lost the World Trade Organization case. This is also this is largely a trade issue between the U.S. and Japan and other countries that have a lot of electronics manufacturing in particular. In the U.S., what's the possibility of acquiring these ores? Most of the U.S. It's heavily associated with apatite mining, so places are in there's apatite mines for agricultural activities. North Carolina, a little bit West Virginia, Colorado. There used to be a company called Molycorp that mined these in the Rockies. Idaho, near igneous rocks that were eroded, and some locations here in China as well. There are some distributed around, but you can see not only are there not places where it's very widely spread. Most of the current active mines are in Colorado, Montana, and Idaho. California has the capacity for some important ones, but the state environmental regulations don't really permit it as well. But you can pull this up. So we have the issue of the ores not being deposited or not being concentrated very much. We also have the issue of the fact that there is not an obvious source for these. In the U.S., it can just be easily turned on and off to match the price manipulation efforts. So, this is an example from the Mountain Pass rare earth element mine in California. This was around on the California-Arizona border for some time. It opened in 1952. It closed in 2002, and ironically, right before this started becoming an issue to the extent of the price manipulation. And this is actually after a series of spills. The chemical processing used to do this, as I mentioned, uses hot acids and things like that, and as a result, spills can be quite devastating. The environmental costs were too great. Most of the people were moving away from this, shutting down the mines. There's been an effort to reopen it, to have more domestic sources of rare earth elements to handle these price manipulation problems, but it's been shut down and open again various times, and basically it's not clear. With the price uncertainty, that it's worth it to build the infrastructure to make sure it can be done in modern, safe, environmental ways. And I think it's probably going to remain closed for much of the foreseeable future. There are efforts ongoing to look for other areas of rare earth elements. One of the areas that's been looked at is looking at deep sea mud from geothermal and hydrothermal vents. So the deep sea mud can often is one of the few places that actually can concentrate these rare earth elements at relatively high levels. They're on what's called manganese nodules. So basically, there's the hot smokers. These are in divergent plate boundaries, right? The smokers come out, they're enriched in various elements, salts and heat, and basically that heat source can actually cause rare earth element minerals to be modestly concentrated above the background, not to the ore deposit level for most things, but the point where you can see these sort of manganese oxide and massive sulfide deposits that'll have relatively high concentrations. They're actually important for the local ecosystem. They're used a lot, not rare earth elements, but these sulfur and manganese deposits for various chemotrophic biological activities. And as a result, there's a growing desire to basically exploit these by, for a variety of different ways. Go to the areas where these massive sulfide and iron nodule deposits were historically left. Particularly 5, 10,000 years old. Near there, and actually mine off the bottom of the seafloor, concentrate them. Of course, there's many other concentrations of other metals there. Things like copper, zinc, even gold is relatively concentrated. By about a factor of 100 times more than it would be expected to be concentrated in normal continental crust. Copper. So there's other things that are additional revenue streams that are worth something there, but the main interest is the rare earth elements. Well, it's not, if the price point gets high again, there's an interest in doing so. If of course it goes back to being low, this could be pretty quickly marginalized. So there are efforts to mine these sort of sulfide nodules, as well as these manganese oxide polymetallic nodules, which are manganese, iron, sulfur, and other reduced forms. So it's been estimated for, the seabed is sort of a buried treasure in a lot of ways. That the seabed near these epithermal deposits and these black smokers might not just be valuable for rare earth elements, but could be valuable for manganese, nickel, copper, cobalt, maybe even gold. For perspective, the sea deposits near these divergent plate boundaries, although it's not obvious you can mine these easily. A lot of territorial disputes, and there's always the potential for big environmental impacts. But the gold deposits within sort of the handful of millions of years on either side of activity in those areas are estimated to be about $150 trillion worth of gold, which is about 10 times US GDP. But of course, that would have to be mined all at one time to do that. So there is a concern, or there is an opportunity, depending on your perspective, that the future will hold a great and vast opportunity for sort of deep sea mining, for meeting our needs to match the population growth and sustainable development of electronics and whatnot, by sort of expanding where we're getting these rare earth elements and other metals from. Other conversations, of course, have been focused on asteroids. I think the ocean's actually probably a little bit more realistic, but the reality is none of these sort of get around the whole point of we have to find a way to recognize that population growth is still our biggest threat. And it's probably not realistic to expect to see, per capita energy, water, and mineral resource use increasing the level it does. So, in theory, you can envision the future will hold a scenario where you have a seagoing vessel has mining units, and maybe even locations for humans to work at, not at these depths, but at below depth, and then have robotic sort of seafloor production tools, as they call them, sort of sweeping the metal-rich nodules off, transporting them back to some sort of lift, and then bringing them up where they can be refined or just hauled back on the vessels. Seems a little bit futuristic, and it probably is. But just so you know, people are starting it as of 2014. 26 licenses were issued in an area of about a million square kilometers. One of the first locations is expected to be up to Papua New Guinea. To my knowledge, although this is still widely talked about, as well as people going to space for various resources, I'm not aware of anyone actually setting up a process like this yet. I'll leave it to you to think about the potential environmental issues. I'll give you a few examples. One of the most obvious ones is habitat destruction. We're sweeping away millions of years of material that gets this area. In a blink, it's going to be very much like mountaintop removal. It's not going to be very likely to be restored. We're going to be mixing nutrient rich deep water, which is going to cause some issues both potentially at the surface and at a depth. We're obviously going to release heavy metals in the mining recovery process into the food chain. If you're deep enough, that may not be as much of an issue, but it's not entirely certain what the whole process is going to be for the areas around these, as well as people working this area. So as I alluded to earlier, other mineral resources that get a lot of attention, particularly for rare earth elements, lithium, cobalt, as well as helium and things like that, is that there could be enormous reserves found in asteroids, comets, etc. Even mining. People talk about mining the regolith of Mars and the Moon, that regulates the dust on those areas to recover resources. And the U.S. Senate did pass the Space Act of 2015. And you probably know there's been more interest in the Space Force in recent years. And the aim is to encourage private research investment in accessing and eventually mining extraterrestrial mineral resources. Again, comets, meteorites, Mars and the Moon's soil or regolith. So there are sort of three classes of asteroids, rich rich in certain resources that are of interest. There's a C class, which is rich in water and bound up in clay minerals. Those clay minerals happen to be particularly rich in rare earth elements, so it's thought to be there's interest there. S class is mainly stony meteorites, or interested in there's interest because of iron, nickel, cobalt, and other metals like that. And then there's another one called the M class, which is extremely rich in metals, and of course they've attracted most interest because of the fact that they would be a truly precious resource. There are people who have already, even Richard Branson of British fame, Virgin Atlantic and Virgin Music, whatever. He's been very vocal about basically funding expeditions and companies to look at the possibility of doing these kind of things. And NASA launched a probe mission, Osiris, in 2016 to land on the asteroid Bennu, and returned with material. That the completion, I think, was successful. The material is not back yet, as far as I know. I think it's not expected back a few years. But this is in the age of exploration. You might catch in my voice, and I'm a little bit not overwhelmingly optimistic that it's going to become a major source of resources for humanity in any of our lifetimes. But if you recognize they're at 7.5 billion nominally, we're gonna keep going to 9 and 10 billion most likely. We're gonna have to find these resources somewhere, and I think that we're gonna go back to sustainability. We go back to water, energy, resources. All of them, we have to make a choice. We have to either stop consuming, or we have to find additional resources, or else find more efficient ways to do the things along the way. So great opportunities for innovation, great opportunities for the recycle, reduce, reuse aspects, and a bright future in all aspects. And maybe some folks in this class or in this generation will be the ones that can lead to some breakthroughs, or we can develop things that are a little bit less consumptive, but still maintain that same quality of life. I think that's the end of the lectures for the course. I'll just leave that slide up so something to look at while I'm talking. That's the lectures for the course. I want to thank you all for participating in what was certainly a tough semester for me. I really enjoyed being in the classroom and interacting with students. So I have to admit, it wasn't as much fun as normal to not be able to talk with all of you and meet you in person and get to see what you're interested in. I hope the course stimulated some thinking and brought some knowledge. I of course really liked the material, but I apologize I wasn't able to be in person. Thank you for participating. I think I'm most impressed with how well everyone's done on the exams, everything like that. I try to keep it straightforward, and hopefully that paid off. I wish you well, and hopefully maybe we can meet in a class in the future. If not, once we're all back on campus, I'd love to meet some of you and learn who was on the other end of the black hole I've been talking into all semester. At any rate, I'll see an exam review pop up probably later tonight or tomorrow. All the other lectures should be online now, so you'll have all the material you need to actually do the remaining worksheets and the last exam. The exam review sheet which is the sort of written descriptions is already online, and I'll do an oral exam review like I had in the past for preparation for the exam. So at this point, all the worksheets that are remaining should be open. All the grades up through exam 3 are already posted, and then you should see you'll probably see an email like this. But I decided, given the change in the schedule of leaving and everything like that, I'm going to open the final exam as soon as the exam review is posted. People can do it at their leisure, and if you want to get out of the way earlier, all the more to you. At any rate, thanks again for sticking with me through the semester. Enjoyed meeting those of you I was able to talk with. I hope you learned something. I hope you got a little bit of interest in the earth sciences and environmental geosciences. Have a great year.